Hello and welcome to MyScience Tutorials. In today's video we are going to be looking at circular motion, and then under this circular motion we'll be looking at angular displacement, angular velocity, and then angular acceleration. And then we'll be looking at the relationship between angular velocity and then the linear velocity, angular acceleration, as well as linear acceleration. After which we'll be looking at the various equations of circular motion and then how to use these equations to solve some practical examples. So without wasting much time, let's get to it. So what is a circular motion? A circular motion, okay, is the type of motion in which a particle or a body moves in a circular path. Okay, so we have a body moving in a circular path, and then that type of motion is said to be a circular motion. Okay, a typical example is a satellite in its orbit is a type of circular motion. Or if we have let's say we have a rope tied to a stone, and then we are rotating this stone at a particular angle, then this is said to be what? A circular motion. Now let's look at some deductions that we can obtain from this diagram. So let me redraw another diagram similar to this, and then let's look at the deduction that we can obtain from it. So assuming we have let's say we have a stone here tied to a knot or a rope, and then we rotate this, okay, or we spin this up to this place. Okay, so we can now join this. Okay, so we spin it up to this point over here, and then we have the angle theta over here, and then the distance traveled from here, okay, to this place is s, which is what? The arc distance. Okay, and then we have this to be the radius of that particular circle. Assuming this is a circle, this is the radius of that particular circle. Now we can see from here we have if we consider this as a right angle triangle, okay, this over here, we can see that we have a distance opposite the angle, and then we have the hypotenuse. So which of the trig functions can give us opposite and then the hypotenuse? It turns out that sine theta, okay, can give us the ratio of the arc distance s divided by what? The ratio the radius r. Now but for small angles, okay, small angles of theta, sine theta will be equal to what? Theta. So in circular motion we normally just use theta to be equal to what? The arc distance, which is s, divided by the radius. Okay, so this arc distance is what we call angular displacement. So this is what we call angular displacement. Okay, so angular displacement, which is the theta over here, is simply the ratio of the arc distance traveled by a body in a circular motion to the radius of the circle. Okay, so this is what we call the angular displacement. Sorry. So with this done with, let's have a look at what an angular velocity is. So angular velocity okay, is simply the ratio of what? Angular displacement. That is, we have, let me use this as angular. So we have angular displacement, okay, divided by time. Now the angular velocity is represented by this a w, is a special one, and then the angular displacement is what we saw earlier on, which is the theta divided by time. Okay, so this is the formula for angular velocity, and then it has the SI unit of what? Radians per second. So it means the angle in this in circular motion is measured in radians, not in revolution. Sometimes you can measure it in revolution, but then we'll be looking at how to convert from radians to revolution, and then from revolution to radians. Okay, so angular velocity has the SI unit, radians per second. But now let's look at something. Okay, we saw earlier on that angular displacement is what the arc distance divided by the radius of the circle. Okay, so if we make the substitution over here, we will have angular velocity to be equal to what? The distance, which is the arc distance, divided by the radius times the time. Now we know from linear motion that what the distance divided by time, okay, is what? Velocity. That is the normal velocity that we know. Okay, so it means this part, okay, the distance divided by time will be equal to what? The velocity that we have over here. So we have our angular velocity to be equal to what? Linear velocity divided by the radius. Okay, so if we make linear velocity the subject over here, we can see that linear velocity is equal to what? Angular velocity times the radius of the circle. So this is the relationship between linear velocity and then the angular velocity of a circular motion. So this is, let's say, equation 3, and then this is equation 2. So angular velocity is what? Angular displacement divided by time. But then again, we can have angular linear velocity being equal to what? Angular velocity times the radius, which means our angular velocity is what? The ratio of the linear velocity divided by the radius. So let's have a look at angular acceleration from here. Okay, so angular acceleration. Now, just like we saw in angular velocity, angular acceleration is also equal to what? Angular velocity divided by time. Okay, so angular acceleration is represented by alpha is equal to what? Angular velocity, which is just w, divided by time. Okay, now we know that from what we just saw earlier on, we know that what? Angular velocity is equal to what? Linear velocity divided by the radius r. Okay, so if we substitute this into this, we have angular acceleration is equal to what? Linear velocity divided by the ratio of what? Divided by the radius times the time. But then we know from linear motion that what? Velocity divided by time is equal to what? Acceleration. That's normal acceleration. So which means this part of the equation, that's velocity over time, is now equal to what? Acceleration. So it means we have our angular acceleration to be equal to what? The normal acceleration divided by the radius. So just like in the case of the angular velocity, we also have over here linear acceleration is equal to what? Angular acceleration times the radius. Okay, so let's this is equation 4, and then this is equation 5. So this the various simple equations that and simple deductions that we can obtain from circular motion, and then the relationship between linear acceleration, that is equations acceleration, that is when we are dealing with straight path, and then when we are moving in circle, this is the relationship between the acceleration. So the linear acceleration, which is the one for the straight path, is equal to the product of the radius in the case of circular motion times the angular acceleration. Now let's have a look at the equations that we use in circular motion to solve examples. So let's look at something very interesting. So we have in linear motion, let's make some comparison over here. So in linear motion, we have three equations. Okay, so the first equation, we know that the final velocity in linear motion is equal to what? The initial velocity plus acceleration times time. Then we have the square of the final velocity is equal to the square of the initial velocity, plus 2 times the acceleration times the distance. and then we also have the distance to be what? The product of the initial velocity times time plus half the acceleration times time square. Okay, so these are the various equations that we use in linear motion, but then the same equation is used in circular motion, but then the only difference here is in place of final velocity and then initial velocity, we use what? Angular velocity 1 as the final velocity, and then angular velocity naught as the initial velocity. Then we use in place of linear acceleration, we use what? Angular acceleration, and then time is still time, so we still maintain that. And then the distance we have in linear motion, we represent that with what? Angular displacement, this symbol. So what we mean by this is what? In circular motion, the final velocity we have over here will be what? W1 is equal to what? W naught plus what? Alpha t, which means W1 squared is equal to what? W naught squared plus 2 alpha theta. Okay, so from here we can have, for this one we have what? Theta is equal to what? W naught t plus half alpha t square. Okay, so this is the only difference between linear motion and then circular motion in terms of using these their equations. So so far we've looked at a lot of formulas. We've looked at angular displacement, angular velocity, and then the relationship between linear velocity and then angular velocity to be this, and then linear acceleration and then angular acceleration also to be this. And we also look at these formulas that are used in circular motion. So let's have a look at some examples to actually enhance our understanding on this topic. So we have example number 1. So we have a rim of a wheel starts from rest and after 20 seconds attains an angular velocity of 6.4 revolution per second. Now calculate its angular acceleration during this period in what? Revolution per second square, and then in B radians per second square. So this is very easy. Let's look at solution. So we have a rim of wheel, okay, starts from rest. Okay, so it means WO, okay, is 0 because at rest the distance covered was 0. And then the question is telling us after 20 seconds, so time is what? 20 seconds. Okay, the angular velocity, that is I1, is what? 6.4 revolution per second. So we have to find the angular acceleration and revolution per second square. So we know angular acceleration is what? Angular velocity, which is angular velocity divided by time. In this case, the angular velocity will be what? The angular velocity, which is the final angular velocity minus the initial angular velocity divided by time, which we know that the final angular velocity is 6.4, okay, minus the initial is 0 divided by the time, which is what? 20 seconds. Okay, so if we punch this into the calculator, we are going to be getting 0.32 revolution per second square. Revolution per second square. So this answers the first part of the question. Now the B part of the question is telling us to get the answer in what? In radians per second. Now if you want to convert from revolution to a radians, 1 revolution is equal to what? 2 pi radians. Okay, so which means in this our example we have 6.4 revolution per second. Okay, so it means this will be equal to what? We don't know. This per second is radians per seconds over here, so we don't know our answer over here, so we represent that with x. So if we cross multiply, it means our what? Angular velocity in radians per second square, sorry, in radians per second will be what? 2 pi times 6.4. okay, then we have our answer in what? Radians per second. Okay, so this is not supposed to be here. So this will be our angular velocity in this example. So for the B part, we have our angular acceleration to be equal to the same formula, so everything will be the same, just that instead of having 6.4 over here, we'll be having 6.4 times 2 pi at the top divided by what, 20. Okay, so if you multiply the angular velocity by 2 pi, then we convert it to radians per second, like I said, and then this will give us what, the top 6.4 times 2 pi. If you punch this into the calculator, we are getting 40.21, then divided by the time is what, 20 seconds, so we are having 2.01 radians per second square as our angular acceleration in radians per second square. Now let's have a look at example number 2. Okay, so example number 2, the question is telling us our body makes 6 complete revolutions in 4 seconds. If it moves in a circle of radius 25 centimeters, calculate I, the linear velocity, and then I or B, the angular velocity. So let's look at the parameters that we have over here. So solution. So we have a body makes 6 complete revolution. Okay, so we have we have our angular displacement to be what, 6 revolutions. Okay, then we have our time. The time it has taken this body to make this complete revolution is 4 seconds. Okay, and then we have the radius to be what, 25 centimeters. So we have to calculate A, the linear velocity. Now we know that the linear velocity V is equal to what, the product of the angular velocity times the radius. So from here we can quickly just go ahead. So we have our angular velocity will be what, angular displacement divided by what, time, multiplied by the radius. So this will give us the angular velocity, angular displacement we have over here is 6 rev. Okay, so we have 6, then times 2 pi, that is, we are converting it into radians, times, so we multiply by 2 pi, then divided by the time is what, 4, multiplied by the radius, which is what, 25. Now because we have the radius in centimeters, we need to convert it into what, into meters. Okay, and then from centimeters to meters, we divide by what, 100. Okay, so this will give us what, let me do it over here. So we have this to be equal to what, 6 times 2 pi divided by 4 times 0.25. okay, so the linear velocity in this case is equal to what, 2.356 meters per second. Okay, so this is the value of our linear velocity in this case. So let me bring this to the top over here. Let me just get rid of it. Okay, so let me write it small here. So this is giving us what, 2.356 meters per second. So B, we have to find the angular velocity. Now we know that from here, okay, from this equation we can make angular velocity here the subject. So angular velocity, the subject, to be what, linear velocity divided by the radius. Okay, and then we already have the linear velocity calculated already. So we have that, which is 2.356, okay, divided by the distance, which is the radius, sorry, which is 0.25. okay, so this will give us what, 9.4 radians per second. Okay, so this is how we solve some practical examples on circular motion. And yeah, this is all I have for you today in today's video. And thank you so much for watching. And then if you are new to MyScience Tutorials, kindly consider subscribing as we post daily video on physics, mathematics, biology, and chemistry. So once again, thank you so much for watching, and I'll see you in the next video. Bye bye.